Hello and welcome. Previously, we saw that modeling population growth with exponential functions is not realistic in the long term because exponential growth functions increase without bound, but in reality, populations do not grow without bound because of the size of their surroundings and limiting resources. Instead, we saw the logistic function and noted that it is a better model for population growth because it grows exponentially at first but levels off later on. Let's find a logistic function that models a real-world phenomena. Suppose a virus spreading through Ottawa County is known to grow according to the logistic model, where t is measured in days. We know the following information: p of 0 equals 2, p of 56 equals 480, and 1,050 Ottawa County residents are expected to get the virus. Determine the values of a, m, and k in the logistic model. P of t equals a divided by the quantity a plus m e raised to the negative kt. We know from our previous discussions that a is the carrying capacity, and because we're told 1,050 Ottawa County residents are expected to get the virus, we know that the function p of t is going to tend towards 1,050 as t increases without bound. So that tells us that our carrying capacity is 1,050 people. We also know that our initial population for the virus is 2 people, because we know p of 0 equals 2. So if we let t equal 0, we already know a is 1,050. We will be able to set the whole equation equal to 2. So we have 2 equals a, which is 1,050, divided by 1 plus m times e to the negative k times 0. This is going to simplify to 2 equals 1,050 divided by 1 plus m. We can multiply both sides by the quantity 1 plus m. So we'll have 1 plus m times 2 equals 1,050. Divide both sides by 2. And then subtract 1. So m is exactly 1,050 divided by 2 minus 1. And we can actually simplify that and continue to have an exact value, 524. If that was not exact, then I would have left it in the previous form. All right, we'll move on to another side to find the k value. So we'll just make a note here. We knew a equaled 1,050, m equaled 524. And so we're going to use this other non-zero data point, p of 56 equals 480. So we know if we set p of t equal to 480, we'll have 1,050 divided by 1 plus 524 e raised to the negative k times t, and t is 56 when the population is 480. So we're going to multiply both sides by the denominator. Our goal is to get k alone. So we're going to have 1 plus 524 e to the negative 56k times 480 equals 1,050. We'll divide both sides by 480. So 1 plus 524 e. Ooh, I lost that negative earlier. All right, we'll correct that. So e raised to the negative 56k would equal 1,050 divided by 480. We'll subtract 1 from both sides. So 524 e to the negative 56k equals 1,050 over 480 minus 1. Then we'll divide both sides by 524, leaving us with e to the negative 56k equals 1,050 divided by 480 minus 1. All of that divided by 524. Then we'll use a natural logarithm in order to undo this e to a power function. So we will end up with the natural logarithm of 1050 over 480 minus 1 all over 524. That's going to equal negative 56k. So our exact value for k, after we divide by negative 56 on both sides, is the natural log of 1050 over 480 minus 1 divided by 524, and then that natural logarithm is divided by negative 56. Notice I did not get out any computing devices. I'm leaving k exactly as is. So let's go ahead and check our answer here. I chose to use Desmos to check my answer. So I entered in my value for A, 1050. That was the carrying capacity. I know that M was equal to A divided by 2 minus 1. So that gives me 524 as expected. And then K equals approximately this value here, 0.10874359. And if we put in our model function for the logistic function, we end up with this blue graph, and we can see it does go through the initial value. At day 0, there were 2 people infected with the virus. After 56 days, 480 people were infected with the virus, and it appears that the carrying capacity is 1050 people. So we can confirm that we did find a logistic model for this data.